Um, Hello everyone. Today I will talk to you about a modern C++ point of view of programming in image processing. First, let us talk a little detour about genericity. Image processing algorithms are not specific to one image type or pixel value, but are intrinsically generic. For instance, the watershed algorithm that we can see on this schematic works on n-dimensional images, on mesh, or on graphs, as shown in the figure. Most of the time, the implementation are restricted to one image type, and those restrictions are not justified. We need to express our image processing algorithms in a generic way so that they work on all image types by default. We need to express them generically. Indeed, a non-generic algorithm grows in complexity depending on all the data type it supports. Uh, here we work. Here we support different underlying. Oh, sorry. Here, here we support different underlying pixel value on these schematics. So you can see here 16 bits integer, doubles, RGB on this axis. We also support different image type here, 2D buffer, 3D buffer, graph, etc. And we support different structuring element shapes. And we can see that the space of possibilities grows with each time we add a new supported type. And if we have one specific implementation for one combination of those types, it's not maintainable. So we say an algorithm is generic when one implementation will work with a large array of different data types. In order to be able to express our image processing algorithm in a generic way, we need abstract image types. These abstractions allow us to extract properties that can be leveraged for behavioral requirements or optimization opportunities. An example of property is the ability here to get an image value from a point. Here we have a loop. We loop over all the points of the image domain, and for one point, we can retrieve the value with image of point. Another key property is the writability of an image. Indeed, it's very interesting to be able to write a new value in an image. Here we have a loop, we iterate over all the pixels, and for each pixel we set the value to 42. Our contribution in this paper is the design of a complex image type named image views. Views are image, they are fully fledged image, they embed pixel-wise algorithms within themselves. They are inspired from millennials morphers and C++ STL ranges. Views are heavily inspired from the functional programming paradigm, map, filter, reduce, and collections. Views aim to completely replace pixel-wise algorithms. But first, what is a pixel-wise algorithm? In image processing, we have three main families of algorithms. We have here the pixel-wise algorithm that is of interest to us. So to compute the value of the output image, we only need the knowledge about one pixel in the input image here. Second, we have the local algorithm. So to compute the value in the output image, we need the knowledge of the input pixel and a window of pixel around these pixels. And finally, we have global algorithms that are a little bit more complex. For instance, we may need the knowledge about all the pixel computed before it, so it's a propagation. We may need a forward or backward pass. We may need to pick pixel inside the image with a specific logic in order to compute this value here. We will not talk about them in this talk. Here we will focus on views that replace pixel-wise algorithms. What is a view? Here is an example of a transform view that performs a binary thresholding of an image. So here we have our base image, U. And we have the the thresholding transformation in the form of the function h. Our view v will hold a pointer to u and a pointer to h. What is important is that when we copy v, we do not make a deep copy of u. We only do a copy of the pointer, so the copies of a view are cheap. Also, as we have a shared semantic of the underlying data buffer, if you went off the scope and is destroyed, V will not point into deallocated data, and we still retain the data like with shared pointer, smart pointer in C++. Another key point is that the resulting image here is not computed when V is declared. Indeed, this image does not exist with this line. This image will only exist once V is completely traversed in a loop and we output the pixel. This is when the transformation will happen. This transformation is lazy computing. And also views are composable. We will get back to it a bit later. So here is another example with the algorithm of alpha blending. Here we can see that alpha blending means we blend one image and another image with a factor, and we blend the two images together into a resulting image. So this is the native C code of naive C code of an alpha blending written in terms of pointers, strides, etc. We have two for loops, so we are restricted to 2D images. And what we want is this. We want to be able to say that my image here is 0.2 multiplied image 1 plus 0.8 multiplied image 2. That's all. We need to be able to write this in one line because we want to be able to reason at image level. Another reason for that is if we want to restrict the working area, the region of interest on the image, we only want to blend one part of the image, we would need to write another prototype of the alpha blending algorithm here, adding 4 new parameters, which means we duplicate the implementation. Whereas with views, we can just pipe another view, which is the view clip, which will restrict the region of interest of an image. This view will return another view, which is an image, which we can pipe directly into the already existing alpha blending here, alpha blending algorithm. And we don't need to redefine our alpha blending algorithm to take into account the fact that we want it to support a regional interest. So the alpha blending in terms of image at image level is written just like this. And we see that it's exactly as in the previous slide. There's just 2 operator multiply and 1 operator plus. The image are taken by copy because it is cheap. So this is very, very simple. Here we can see that this is the AST, the computational tree that will be executed when the view here in blended, the view is traversed and the values of the pixel are requested. So this is what we want. We are reasoning at image level, and we have simplified the way to write pixel-wise algorithm. So we said earlier that views comes from the functional paradigm. They are heavily inspired by the functional paradigm, functional programming paradigm. Sorry. Here are the domain restrictive views. So we have filter, we have clip, we have mask. We have already seen clip to restrict the regional interest of an image. And here are the value transforming views. So we have transform view that we have seen, we have zip, cast, plus, multiply, etc. All of those are views. Let us do a particular focus on the zip view. Indeed, the zip view combine two or more images as input into one meta image as an output. And this meta image has its value as tuple that references value in the original images that were combined. This is very particularly useful because there's a pattern in image processing that comes every time. It's iterating over an input image and an output image at the same time on the corresponding pixels to compute something from the input image and put it in the output image. So the view zip is always preferred to do this kind of loops. We said that we leverage properties. We have seen that view, there are two interesting properties, writability and accessibility, that we have seen earlier. But there are also other properties that views may or may not propagate when we change them. So there is the row property. The row property is a direct access to the underlying data buffer with the stride informations. We have the indexable property, which is an access to the pixel of an image via an index k when we know the number of pixels there is in an image. And there is the bidirectional property, which is just a way to say that we can traverse our image backward and our image forward. There are algorithms that require this property. So what is interesting is that the row property is never preserved when we are passing an image into views. Indeed, we lose the information about the pointer of the underlying data buffer and the stride informations. So after a view transform, we can't go and access the raw data buffer. However, the writable property may be preserved, and especially is preserved with domain restricting views such as clip, mask, and filter, but is only preserved in special case with value transforming views. So it's preserved via zip. We have seen why. Zip just combine images, but does not modify really the value of those images. And there is the transform view. The transform view will preserve only if the function func here is a projection function. So if we have a triplet RGB and our func is a projection over the red channel, if we assign a new value for the red channel, we can assign it back into the RGB triplet. But if we have the same RGB triplet and that our func is a grayscale transformation, if we assign a value into the grayscale transformation, into the grayscale transformed image, we can't get the RGB triplet back from this grayscale value. It's a whole field of research on its own, and it's called the recoloration of image. So we can preserve all the time with transform the writability property. We want to validate our design. So to validate our design, we need to validate 2 points. The first point is we want to reason at image level, so no row for loop over pixels. The second point is that it's a new abstraction and we are doing it in C++, so we want a zero cost abstractions. How do we do that? We use a pipeline, a concrete pipeline with which is the background subtraction pipeline. So here is an example. So we have a background, we have an image with a foreground, and we extract this foreground by doing a subtraction. So this pipeline is modelized this way with algorithm. What we can see is that there is blue dots, and each of these blue dots are temporary copies within the algorithm that will increase the memory consumption. Whereas if we write this pipeline in terms of views, we can see that there are a lot of transformations that can be done with views, and there is only one blue dot here, so there will only be one intermediary image in memory. The code of this pipeline in terms of view is shown on this slide, and we can see that there is no row for loop over pixels. So here we validate the fact that we reason always at image level when using views. This table presents the results of our pipeline. So we can see that we are within the standard of the industries with the OpenCV. We can see that the computation time is the same, is roughly the same with the standard deviation taken into account. So we have a zero cost abstraction, and the memory consumption is halved. So we have validated our design. To wrap up, we have showcased a new abstraction layer, so image views that are fully fledged image type embedding image processing algorithm. They reconcile genericity, efficiency, and ease of use. They allow the practitioner to reason at image level with no raw for loops. It leads to performance gains through decreasing memory consumptions. However, views rely on C++ template metaprogramming, whose instantiations may lead to code bloat and increasing binary size. Templates belong to the static world, which fully interoperate with the dynamic world, Python, where most of our target audience, the image processing practitioner, reside. We rely a lot on the compiler to optimize the code to all the zero-cost abstraction rule. But when the compiler fails us, it greatly impacts the resulting performance. Views are implemented in Python, and here is a link. Thank you for your attention. Do you have questions?
Do you have questions? Michael, I have a question. So when you
Yes.
use templates in C++, it's always very difficult using them because if something goes wrong, you showed this matrix which operations can be used for your views. Then you get very cryptic messages from the C++ compiler. Can you elaborate what you're doing to help the users of your template library?
Yes. So this work is inscribed in my thesis, and the first part of my thesis was to design a framework of concept in C++20 just to solve this problem alone. So we have made a complete framework of concept in modern C++, so that we get meaningful error messages, and we have built this abstraction on top of those concepts, so that the user can leverage the property properly and not rely on cryptic techniques such as spinae, etc., that leads to horrific error message like you said. So we have already built upon that.
Thank you for your presentation. I have a very simple question. And do you have any insight that we can apply to the other language other than C++? Like any insight did you get during your research?
Uh,
Maybe
can
it's better to kind of out of scope.
I have trouble hearing the question. I'm sorry. Um, can you get maybe near the microphone?
Do you have any insight that we can apply in other languages?
Ah, um, in other languages, Is there an insight of?
Uh-huh. Oh, sorry. Yeah, keep going, please. Michael,
y-
did you hear? Should I go on?
Michael, can you hear us?
Yes, yes, I can hear. Yeah,
Did you understand his question? Well, should he repeat?
not very, not very
Uh,
much. Sorry.
he's asking about also your work is very heavily relied on C++, and he's
Mm-hmm.
asking, well,
Well,
yeah,
it's just a very simple question. And if do you have any insights or how to say maybe insights you have you found in your research? No insight that we can apply in other languages other than C++.
yeah,
Yes. Um, the insight is that C++ relies on parametric polymorphism to aim for zero cost abstractions, to reach the goal of zero cost abstractions through the C++ compiler that does a lot of optimizations. So my insight is that if you don't aim for efficiency at all costs, you can always in other languages that rely on, for instance, polymorphic based on trait like Rust or interfaces in Java to require behavioral patterns, you can always reach this goal, but it will cost you a little bit in performance. So this design should be, in theory, language agnostic. There will be limitations in each languages to these designs, but I think you can mostly work around them most of the time. However, if you want really zero cost abstraction, sadly, uh, you should rely on C++. Maybe in Rust with traits, you can reach real zero cost abstractions, but I haven't done the tests right now. So it's a future goal to see what Rust has to offer.
Thanks so much, Michael. And let's thank the speaker.